Today we're going to continue our discussion of confidence intervals. So last time we saw that when the population standard deviation sigma is known, then we can construct a confidence interval for our population mean mu, and we do this using a sample of size n with mean x bar. Right? And what we say is that with C% confidence, so C is our confidence level, which is usually given to us. So with C% confidence, we know that our population mean mu is between, we take our sample mean, x bar, minus some margin of error. So mu is between x bar minus e and our sample mean plus the margin of error, where our margin of error, e, is computed as our critical value times sigma divided by the square root of n, right? Where n, of course, is our sample size. And remember this critical value, z sub c, this is the critical value for a C% confidence level. Now the z value, it's basically just a z-score. What it's really saying here is if this is our standard normal curve, so we have 0 in the middle, then if this is the z-score, z of c, then on this side this would be z of negative c. And what it's saying is if we go between these two z values, then we get C% of the total area. Or in other words, our area in between these z values is c. So if we had like a 90% confidence interval, then our area here would be 0.9. And what we do is we go and find that z value, which is just given to us in a table. We saw how to find the critical value last time. Well, now today, suppose our standard deviation for the population is unknown, right? Which is usually the case. I mean, if we don't know the population mean, then we usually don't know the population standard deviation as well. So in this case, in order to come up with our confidence interval, we have to use the sample standard deviation, S. Right? And what we can say is that with C% confidence, so that's our confidence level, right? Then our population mean is going to be between, again, x bar minus some margin of error and x bar plus some margin of error. And our margin of error this time, our formula is a little different, but very similar. We get, instead, we're going to call it T sub c, and this here is a critical value for what's called the student's T distribution, which we will discuss a little bit more in just a minute. But let's finish our formula. So we take this critical value and we multiply by, since we don't know sigma, instead we use our sample standard deviation, and then the denominator will still have the square root of n. Okay, let's take a look at this student's T distribution and see how we actually find this critical value. So just a little bit about the student's T distribution. There's many T distributions, and it all depends on the sample size. And so if we have a small sample size, then this is kind of what our T distribution looks like. It looks kind of like a normal curve. It's bell-shaped, but these tail ends are much thicker, right? And if we increase our sample size, well, then our curve looks even more normal. And if we let our sample size approach infinity, so it just gets larger and larger, then eventually we will get the standard normal distribution. Okay. And so that kind of gives you an idea of what the student T distribution looks like. But what we really need to know is how to find this critical value. Okay. So in order to do this, there's two things we have to know. First, we have to compute what's called the degrees of freedom, which is not hard to do. Degrees of freedom, which I'm going to abbreviate DF, is just equal to the sample size minus 1. That's it. Okay. And now, using our degrees of freedom and also our confidence level, so those are the two things that we need. So using degrees of freedom and confidence level C, which is always going to be given to us in the problem, right? We have to look at the table on page A24. So it's in the appendix. It's right after the standard normal distribution table. All right, so let's take a look at that. Here it is. Okay, so notice in this table here we have our degrees of freedom. So that's all of these numbers here. And then our confidence level C, those are all of these numbers in this row here. So suppose, for example, we had a sample size of 20. Well, that would mean that our degrees of freedom would be 19. And suppose we wanted a confidence level of, say, 99%. Well, that would be equivalent to 0.99. And so here we go. This would be our critical value T of C. All right. Let's look at an example. So here's our example. We have a random sample of 144 elephants with a mean weight of 12,000 pounds and standard deviation of 300 pounds. And we're going to find a 90% confidence interval for the population mean weight, mu. Okay. Now first I'm just going to identify some information here. Notice our sample size is 144. Right? Our mean weight, and this is for the sample, so sample mean is 12,000 pounds. And our standard deviation, and notice this is the sample standard deviation. So here we have that S is equal to 300 pounds. Right. And we're going to construct this confidence interval, and we're going to break this up into a few steps. First, let's find our degrees of freedom. And so remember, degrees of freedom, that's just the sample size minus 1. So in our case, we'll have 144 minus 1, which is 143. And now we want to find our margin of error. And so remember, our formula here is we find the critical value for the t distribution times sample standard deviation over the square root of n. And in order to find our critical value, again, the two things we need to know are the degrees of freedom, which we know is 143. We also need to know our confidence level that we're interested in. We were asked to construct a 90% confidence interval, so that means our C value should be 0.9. All right, so now let's refer to the table. We're going to use these values to find our critical value. So here's our table. Again, our degrees of freedom is 143, and our confidence level is 0.9. All right, so if we come down to our degrees of freedom, notice we don't have 143. We have 100 and we have 500. So what we need to do is we're going to pick the closest integer that is smaller than our degrees of freedom. So in that case, that would be 100. And let's see, our confidence level should be 0.9. So that would be this guy here. And where do this column and row meet? I believe it's this value here, 1.66. So that is our critical value, 1.66. All right, so we know T of C is equal to 1.66. And now let's finish computing our margin of error. So we'll have 1.66 times our standard deviation, which is 300 pounds, divided by the square root of n, and n is 144. And if we plug this into a calculator, let's see, this is 1.66 times 300 over 12. Plugging this into a calculator should give us 41.5. And of course, this is in pounds. Those are our units. And so now we're ready to construct our confidence interval for mu. And what we can say is with 90% confidence, mu is between x bar minus e, which is going to come out to, let's see, x bar is 12,000 pounds, minus our margin of error, which is 41.5 pounds, which gives us a difference of 11,000 958.5 pounds. So that's the lower end of our confidence interval. And our upper end is going to be x bar plus E. So 12,000 plus 41.5, which comes out to 12,041.5 pounds. Right. So mu is between these two values. All right. One more thing we should note, in order to use this method of using the t-distribution, we need that one of these conditions hold. So it's appropriate to use this method if at least one of the following is true. Either the distribution of x values is approximately normal, meaning it's symmetric in mound shape, or if that's not the case, if our distribution is, skewed left or right or bimodal, well, in that case, we need to make sure our sample size is at least 30. And there we go.